You said that wheel graphs are star and mesh.
Hmm.
What's was it star and mesh or
No,
ring and mesh?
no, not star and mesh. Uh, mesh graph is the complete graph. Okay, mesh graph is the, in this graph theory we call complete graph. And what another graph was wheel. So
Yes.
wheel graph, you can uh, wheel type of graph, you can call this star. Okay, wheel type of graph means there will be there will be uh, the outline border, and there will be one vertex in the center. So this will be called wheel. So in that computer topology, you can call this star, isn't
What's
it?
the in star? The like the computers or the nodes at the side, they are not connected with each other. Like every one is connected to the middle one, but not with each other, within each other.
That is the point. That is why you can say this is star and also cycle, That is, you call this in the topology, you call this
Star and
ring,
ring.
ring. You call this ring. Okay. Wheel means ring, star together. Okay. In the graph theory chapter, we call a ring as a cycle. We call ring as a cycle. Cycle is another type in the graph theory. It is called a cycle, and which is comparable to ring. And if you combine together a ring and star, that can be called wheel. Is it okay now?
Yes, sir.
But mesh is different. Mesh is complete graph. Mesh is everyone is connected with everyone. So that is your question. Let me now go to the bipartite graph. So there maybe, I mean, uh, this is one example, say like that. Okay. So what you can do, what you can start with, you can start with any point. You can start with any point. If you think the vertices are A, B, C, D, uh, E, F, then you start with any point. Say you are starting with F, no problem. So you start with F, and then you put other points in the other side. So A will be in the other side, there is one connection, and E will be in the other side, there are two connections with E. So A and E are in the other side. And you will go with next, that is E, D is one thing, but you have EA also, EA. So when you have EA is connected, this line, when you have EA is connected, then it is not bipartite, because in the bipartite graph, the connection between the points in the same group is not allowed. Connection between the points in the graph in the same group, it is not allowed. So you see this one, so you will say no, it's not bipartite. Say we do not have this, say we do not have EA, then you continue. If you do not have EA connection, then you continue with the other points, like E has a connection with D and E has two connection with F, then fine. Now go with D. D has a connection with A, so it is not a problem. D has a connection with A, fine. And D has connection with E, that's it. Okay, now you go with uh, A point. A is F and D and C also, and C also. So there will be another point in the other group, that is AC. AC, fine, and also AB, also AB. So if you have AB, then B has to be here. B has to be here, the other group. So again, there is a problem because BC is connected again. So you see BC is connected. That means BC will be the connection within same group. So it is not possible, it is not applicable. If it is there, then you will say this graph is not bipartite. This graph is not bipartite. If it is not there, then fine, you will say okay, then it is bipartite. So that is the understanding. Is that clear?
Yes, sir. So also,
So
sir, there can only be two groups.
yes, only two group because by means two. So
Yes, sir.
by means two, by part. By part means two part. Okay. So that is all. Now we will talk about another thing. It is also similar. This is called isomorphic graph or isomorphism. Okay. So isomorphic graph or isomorphism. Uh, this is like one graph can be presented in a different way. It will look different, but they are the same graph. So you can say this is the same graphs, okay, or same graph uh, presented in presented in uh, different ways, different ways. So you can say like that. And how you can check the two graphs are isomorphic or not. So you can write two graphs are isomorphic if uh, they have the same degree sequence, and also they will have the uh, same adjacency matrix. So two graphs can be isomorphic if they have the same degree sequence, and if they have the same degree sequence. So this is one point, and uh, the same adjacency matrix with 1 to 1 mapping. Okay? So this is the theoretical concept. Now what is it? Say I'm giving you example. Say I'm taking a graph like this. So this is a graph, 4 vertices, and these are the connections. And if I just do the graph like this, and uh, where is this? Okay, and I'm also Okay, let me just do it in this way. I'm just trying to making it smooth in the circular line. That's all. So, what do you think? These two graphs are uh, same or not same?
Yes, sir. Isomorphic, sir.
They are actually the same graph, but they looks a little different. So if you, I mean, carefully look into the two graphs, then you will understand. Okay, there are four vertices and how they are connected, all the same. So what is degree sequence? Degree sequence is the degrees will be written. Oh, in this case, same degree. Okay, fine. Let me just write. No problem. So degree sequence means all the degrees are written one by one, serial order, highest to lowest. So what is the degree of this point? If the points are A, B, C, D, what will be the degree of A? That will be 3, right?
I'll give it 3, sir.
What
Yeah,
will be
3.
degree of B? Again 3, C, again 3, D, again 3. All the same in this example. So if you think about degree sequence, that will be 3 comma 3 comma 3 comma 3 because all are the same. But if it is not same, then you write highest degree first and then in order. Okay, then lower, then lower, then lower, then lower, like that. So degree sequence of the first graph is also 3, 3, 3, 3. Second graph is also 3, 3, 3, 3. So this is all the same, right? Let me take another example. Let me do another example. Say uh, something like this. Okay. Okay. Um, say there is a point here. Let me just take it like that. So this is one graph. And if I just make this graph in a different way, just like this, and oh, not here. Okay, will be like this, and something like this. So you can say, well, the graphs, two graphs does not look same. They are presented in a different way, but actually they are the same graph. But actually they are the same graph. Think about two graphs. Can you understand they are the same graph?
Yes, sir. Because they
Yes,
are
sir.
basically associated.
So what will be the degree sequence? You can just think about degree sequence now. For the first one and second one will be all the same. So how?
So
Say this
4,
is
3, 3, 2.
4, okay, and then it is 3 and it is 3, and this one is 2,
2. Then
and
sir,
this
1,
one is
1.
1, 1,
1,
1,
1.
1.
The
So
middle
you
is
will, middle one is 2, yes. So you will start from 4. You will write 4, then comma, then 3,
3.
then 3, then 2, then 1, then 1, then 1, then 1. So 4 ones. So this will be the degree sequence. How many degrees? 1, 2, 3, 4, 5, 6, 7, 8. because there will be 8 points. So 1, 2, 3, 4, 5, 6, 7, 8 vertices. So in this case also, for the second graph also, you will have the same degree sequence. So same degree sequence means one will be 4. So this one is 4, and this is 3, and this is 3, and this one is 2, and 1, 1, 1, 1. So you are getting all the same degree sequence. So this is a first checkpoint. This is the first checkpoint. If you see same degree sequence, then the two graphs maybe, it is not always, maybe uh, isomorphic. May not be, because you need to check the adjacency matrix also, and that should be 1-1 mapping. 1-1 mapping means exactly same presentation of the matrices. You already know how the adjacency matrix you can make. So how the adjacency matrix you can make? You can make the adjacency matrix by vertices, right? So vertices like A, B, C, D, E, F, okay, G, H, something like that. And in the column also A, B, C, D, E, F, G, H, like that. So you will put the number of lines with A and A. So no line A, B, how many lines you will put, A, C, how many lines you will put, something like that, right? So if you uh, name the points A, B, C, D for the first graph in a way, say A is 4, then B is 3, then this one is C, so that will be 1, and this one is, so that will be 1, and this one is E, so it will be 3, and F will be 2. In the other example, if you give the names like this one is A, so it is 1, and this one is B, so it is 3, this one is C, so it is 4. So you may write A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, H, but the serial of numbers will not be the same numbers, right? So if you change the position of a row, say whole row is changed here after C point. So is it a problem? No, it is not a problem. You understand what I'm saying? Say one
uh,
matrix is 0, 1, 3, 2, and 3, 1, 0, 2. I'm just taking one matrix, any matrix. Say 2, 0, 1, 4, and 3, 1, 2, 5. Say this is our matrix. And if I change one column, if you change this whole column from this position to another position, say here, is it a problem?
no,
This will not be a problem. This will not be a problem. If you change the row also, this row is changed to here. So this will not be a problem, because in the matrix actually every column, every row has a meaning. Every column, every row has a meaning. So in this case, you have the same row and column, all the vertices, the columns also ABCD and rows also ABCD. So in that case, if you change A, you will also change this A. Okay, so you can change, no problem, that is not a problem. So if you change suitably, say C is 4, so this will be A. So A will be 1-1 mapping with C point, and this B will be 1-1 mapping with B point, and this E, that is 3-degree vertex, will be 1-1 mapping with this 3-degree point. Okay, you understand my point. So 1-1 mapping means every vertex will be mapped with the similar vertex in the other graph. So when it is possible, then you can confirm, you can surely say that two graphs are isomorphic graph. Otherwise, degree sequence is the first check. This is the first checkpoint. So if degree sequence is not same, then you cannot or you do not need to check the other things. So if degree sequence is same, then you need to check the adjacency matrix. Okay, so it is the first checkpoint so that you can be sure the graphs can be isomorphic or may not be. Okay, say let me tell you another thing here in this same example. So another thing is, say for example, you have the same graph but little different, like say this is not here, this is not here. Say this one, the corner, this one is here. So what will happen? In this case, degree sequence will be same. Degree sequence will be same. How? Because this one, this corner is 3 now and this corner is 2 now. So if you write the degree sequence, you start from the highest one. So you start from 4. So you write 4 first and then 3, then another 3, isn't it? Same degree sequence will come. 4, then 3, then another 3, then 2, then 1, then 1, then 1, then 1. 4 ones and 2 and 3, 3 and 4. So this will be same degree sequence like the first graph. So first graph, second graph, degree sequence same, but they are not uh, the isomorphic graphs. Why not? Now you can check why not.
Sir, maybe sir, both three middle was two, but here both three middle was not two.
Yeah, so this is not the same construction. This is not the same construction. Say, now we are thinking of a real example. Say, this A computer, this is a computer, this is the computer in the, say, BC SAR's office. Okay, in IUBAT, the 4, that means this A computer is our VC SAR's computer. So this is the VC SAR's computer. I can write it, okay, this is our VC SAR. Okay, fine. And this one is, say, our Pro VC madam. Okay, this is our Pro VC madam. And this is our treasurer madam. Say this is our treasurer madam. Okay, so these two is another computer. This is say accounts. This is say accounts. Okay, and other connections. Now, what do you understand by this? You understand that VCSAR does not have connection with the accounts section. VCSAR has 4 connections. One is with treasurer madam, one is with provici madam, and other 2, we do not know other 2, but he does not have the connection with accounts. Accounts has 2 connections. One is provici, one is treasurer. You understand what I'm saying? So in this case, the 4 degree computer should be VCSAR. Okay, so find VCSAR. and 3 is provici and 3 is treasurer. So do you think it is the same thing here also?
No, sir. Here, province is not isn't does
So
not have any connection with the account.
so accounts should have the two connection, but here the VCSR has the connection with accounts and VCSR has no connection with treasurer madam. So these two are not isomorphic, but they are same. I mean, they are with the same degree sequence, 4 3 3 2 1 1 1 1, but they are not isomorphic. Is it okay now?
Yes, sir.
Yes, sir.
So this is the concept of isomorphic graph, and that is all. And I will. Oh, okay. I have not enough time. So let me just tell you something, then you will understand. Let me just tell you something with this example so that it will be okay. Say we have the names. Okay. The other thing what I want to tell you today is called path and circuit. So just definition, I will talk about more on path and circuit in the next class. So what is path? What is circuit? So path means the path and circuit, both, actually both. Okay. So let me just write it. Both are actually sequence of vertices. So sequence of vertices in a graph. Okay. So you may include all the vertices, you may include some of the vertices, does not matter. Path is the uh, starting and ending vertices are different. So that will be called path. Starting and ending vertices are different. And circuit means this is also the sequence, but in this sequence, starting and ending vertices are same. So uh, whichever whichever corner you start, you will come back to the same starting point. That will be circuit. So how it is being done? Let me just have some name. So when you write the sequences of the vertices, you will write the next vertex if they are connected. If they are not connected, then you will not write the uh, vertex. Say this example we are taking, and let us put some name so that it will be easy to write the sequence of vertices. Say the points are like A, B, then C, then D, E, F, G, H. So there are 8 points. So A, B, C, D, E, F, G, H. Now, about path example, you can write A, comma, C, comma, D, comma, F, comma, G. Finish. Possible. You can write B, comma, C, comma, G, comma, H. Okay, possible. You can write D, comma, F, comma, G, comma, H, comma, G again, comma, C, comma, B. Possible. So there are many paths possible like that. And the sequence, okay, and the sequence will be, you start with one vertex C, D, F, G, C. Okay, you start with any other vertex, say G, then H, then G again, then F, then D, then C, then G. I mean, you have to start and end at the same vertex point. So you can say like E, then D, then uh, C, then G, then F, then D, then E. So that will be another example. So in this way, you can have many circuit examples. Is that okay? Just keep this in
Yes,
your mind, and in the next class, I will talk more, and there are theories on this. So we will talk about the path and circuit related theories. Okay, so that is it for today.